All right, we're going to talk about addition today, how we can build circuits that will do addition for us. And this is arguably a pretty complex topic because we're going to go beyond the kind of development we've been working with so far, where we start with a truth table and we write, an expression and we minimize it and so on and so forth. Today we're going to design a circuit and we're going to do something like we do in coding. We're going to build it up out of simpler building blocks. So our goal is to construct a circuit that will take, a pair of binary numbers and produce a sum. For example, 1 plus 1 is 0, 1, 0, 0 is a 1, 0, 1 is a 1, that's a 1. So if we ignore 2's complement, if we just think of these as plain old numbers, this is 9 plus 5, and we should end up with 14. And this is obviously a useful circuit to have when we're building something like a computer, so that our computers can add numbers together. So if we try to go about this in our usual way, let's just think about a 2-bit adder. So, start with a system diagram, and let's imagine two numbers coming in. So I'm going to call this A1, A0, B1, B0. A1, A0 is input number 1, and I'm going to say A1 equals the most significant bit, right? So if it's a 1, 0, that's the number 2 as opposed to the number 1, 0, 1. And then B1, B0 is input number 2, and we're going to produce an output. Well, if we add two 2-bit numbers, the largest 2-bit number we have is 3. 3 plus 3 is 6. That takes 3 bits to represent. So we're going to have 3 output bits, and I'm going to label these S2, S1, 0. That's our output, which is equal to A1, A0 plus B1, B0, where this is addition, not a simple logical OR operation, and S2 is our most significant bit. All right, that's the goal of our add circuit. And so we can make a truth table to describe this, A1, A0, B1, B0. And we can describe what the output should be. And we're kind of, getting 3 truth tables for the price of 1. I'm going to write all 3 of our output variables in this one table. And I'm skipping a bunch of values here. Part of your exercises are going to be to create this table on your own. But let's see how we would fill in this table. Because we're doing addition, right? So if we sort of break our input up into 2 pieces, right, each input corresponds to a certain value of A and a certain value of B. So this first row, A is the number 0, B is the number 0. The second row, A is 0, B is a 1. Here A is 0, B is a 2. Here A is 0 and B is a 3. In this row, A is a 1 and B is a 0. In this row down here, A is a 1, B is a 3. Here A is a 2, B is a 0. Here A is a 3, and B is a 1. And here A and B are both 3. So each of these 16 inputs corresponds to a pair of values, right? A value for A and a value for B. And so I'm writing out, in decimal notation what the value of A and B is. Why? Because I want to add these together. And we add decimal better than we add binary. So what's 0 plus 0? 0. 0 plus 1, 0 plus 2, 0 plus 3, 1 plus 0. 1 plus 3 is 4, 2 plus 0 is 2, 3 plus 1 is 4, 3 plus 3 is 6. So I've skipped a bunch of rows. You can fill those in. You'll do this on the practice problems. So here's what we want our circuit to produce, these values. Well, our circuit, produces a binary output, 3 bits. So let's write down what the values of S2, S1, and S0 should be to represent each of these sums. Well, this is, the number 0, the number 1, the number 2, the number 3, the number 1. Here we want the output to be 4, so we should output a 1, 0, 0. Here's another 2, so 0, 1, 0. Here's another 4, so 1, 0, 0. And our last output should be a 6, that's a 1, 1, 0. All right, so, we can ignore all of this stuff and just think of this as a truth table, 4 inputs, 3 outputs. But we wrote these other columns to help us figure out what these outputs should be. All right, so now we've got a truth table, 4 inputs, 3 outputs. We could make 3 K-maps. We could, look at this as a truth table that generates S2, make a K-map for that, covered with rectangles, write equations. And then just look at S1, make a K-map for that, covered with rectangles, write equations, and then S0. And if we do that, we're going to get 3 pretty complex equations. There's going to be some checkerboarding going on. And this is going to be a lot of circuitry. And you're going to do this in your practice problems. You're going to do this in one of your labs, and you'll see how complex this can get. But this is where we say, hey, maybe there's a better way to do this. And the better way comes from how we add things as humans. We don't just go into some circuit in our brain and say, oh, if we have these 4 inputs and these 4 inputs, here's what the output is. We follow an algorithm. We say, let's add these 2 bits, let's write down that digit, and then if there's an extra 1 coming out, let's remember it and add it to the next 2 bits. Well, we can take that algorithm and we can create a circuit that basically follows that algorithm. And so we're going to, instead of building our circuit by just doing, a sum of products on 3 big truth tables, we're going to use a different approach. And this is based on the idea of a half adder and a full adder. So let's start with what a half adder looks like. Half adder has 2 inputs, A and a B, and 2 outputs, a sum and a carry. So A comma B are input bits. S is an output sum bit. C is an output carry bit. This is a circuit that basically does this. Adds these 2 bits, generates a sum, and figures out what the carry is into the next stage. And this is not a bad circuit to design. Because, with only 2 inputs, there's only 4 possible combinations. And if we, have a 1 and a 1, we've seen our sum is a 0 and our carry is a 1. But if we were adding and we had a 1 and a 0, our sum would be a 1 and we would not have a carry into the next stage. So 1, 0 gives us a sum of 1 with no carry. And the same thing with 0, 1. And if, the 2 bits that we're adding together are both 0, we end up with a sum of 0 and no carry into the next stage. So there's the truth table for a half adder. And we can use this to add our 2 least significant bits, generate this least significant bit of the sum, and figure out what the carry is into the next stage. Now we can't use this half adder to add this next column because we actually have 3 things we have to add. A, B, and whatever carry we had coming from the previous stage. So we need a slightly more complex circuit, and this is called a full adder. And a full adder looks like this. there's an A, there's a B, there's a carry in, and on the output side there's a sum and there's a carry out. A, B, and C are input bits. S equals output sum, C equals output carry. And we can design a truth table for this. And it's a little more complex because we've got 8 possible combinations. But we can go back to, an example. So for example, in the second row we had a 1 coming in as a carry and we had 2 zeros for A and B. The result was a sum of 1 and a carry of 0. So if A and B are 0 and we have a carry coming in, our sum is 1, our carry is 0. And we can try this in all possible combinations. If we have a 0 carry and we're adding 2 zeros, we get a 0 and no carry to the next stage. And 0, 1, 0 is the same. If we have an incoming carry and we're adding a 0 and a 1, what do we get? 1 plus 1 is 0, and we get a carry to the next stage. So A is 0, B is 1, and a carry coming in, we get a carry and a sum of 0. And so we can do that analysis and figure out all 8 combinations, including the last one where we had a carry of 1 coming in, and we were trying to add a pair of 1s. 1 plus 1 plus 1 is 3. Well, that's going to be a sum bit of 1 and a carry of 1. So that's why this case we have a sum of 1 and a carry of 1. So this is our full adder. All right, so we've got a pair of building blocks, half adder and a full adder. And it turns out we can put these together to build larger adders. And it works like this. So I'm going to flip these around and put the inputs on the right and the outputs on the left. So here's going to be a half adder. And I'm going to put in 2 inputs, A0, B0. I'm going to put a sum coming out here, which I'm going to call S0. So here's, our A and B inputs and our sum. I'll call that S0. And here I'm going to make a full adder. And it's got a pair of inputs, A and B, and it's also got an incoming carry, and then it's got a sum that goes out and an outgoing carry that goes like this. Alright, so into here I'm going to feed bits 1 of my 2 numbers, A and B, and the carry out from my half adder, I'm going to connect that to the carry in on my full adder. I'm going to take the sum from my full adder, call it S1. I'm going to take the carry and call it S2. And if you work through this with some examples, what you'll find is that this is a block diagram for our 2-bit adder. If I take the least significant bits of A and B and put them into here, this sum coming out is the least significant bit of the sum. And then the carry coming from here, if I put that into the carry input of a full adder, and I add the most significant bits of A and B, the sum coming out of the full adder, that's that middle bit of my 2-bit sum, and the carry coming out of the full adder, that's the most significant bit of my 2-bit sum. Alright, that's the high-level overview of how this works. You're going to do this in a lab, you're going to do this in practice problems. But while you're doing those, don't just follow the steps mechanically. Think about what you're doing and why. Think about what a half adder looks like. Think about what a full adder looks like. What you want your 2-bit adder to do, and how this is getting the same behavior that you could get by making a big long truth table. But instead of just blindly making a truth table with 4 inputs, 3 outputs, we're functionally describing how we add 2 2-bit numbers and then building a circuit based on that functional understanding. And this we could extend indefinitely. We could make another full adder and another full adder. And we can keep chaining these carries together. And there's a 4-bit adder. You put in your least significant bits, bit 1, bit 2, bit 3, and you get out 4 sum bits plus a final outgoing carry. So you can cascade these together and get what's called a ripple carry adder. And it's not very efficient for long input numbers because, you know, when we do pencil and paper addition, we do one column at a time. We don't know the final answer until we've done all the columns. So if we try to add 64-bit numbers like this, while we're doing our first 63 calculations, we have no idea what the 64th bit will be. And we don't know it until we've done all 63 columns before it and then added up that 64th bit. And the reason we don't know that is because we don't know what that final carry will be going into the 64th column. So this is a slow way to do addition in circuitry. Towards the end of the course, we'll touch on some other designs for adders, including something called carry look-ahead adder, which takes care of the problem of this ripple. But for right now, for this part of the course, we're just worried about a 2-bit adder. So we're going to take the half adder, full adder, put them together, and build up our circuit like that. All right. So let's continue talking about other kinds of more complex logic blocks. So I want to talk about something called a multiplexer, or sometimes just called a mux. And muxes are extremely useful circuits. They do something like take a collection of inputs and choose one to pass to an output. So for example, a 2-to-1 mux. We can think of as having 2 inputs. Let's call this input 0, input 1. And then we have some kind of select input. And then we have a single output. Now, we could write a truth table for this, but there's a functional way to understand what this circuit does. If S equals 0, then input 0 gets sent to X. If S equals 1, then input 1 gets sent to X. So this is a steering circuit. This is a way to sort of have kind of a mechanical switch inside that either connects input 0 to the output or connects input 1 to the output. And how do we choose which one is connected? By choosing a value for S. If S is 0, it's like there's a connection between here and the output. If we change S to a 1, there's a connection from input 1 to the output. And this turns out to be really, really useful when we're building things like computers. In fact, the central part of most central processing units, CPUs, is really a bunch of multiplexers steering data around a collection of subsystems inside the CPU. Now, how do we create a mux? We don't need to do anything magic. We don't need to actually move a wire from here down to here. We can describe this with a truth table. We can say input 1, input 0, select, and what's our output X. Well, anytime select is 0, our output should match I0. So here it should be a 0, here it should be a 1, here it should be a 0, and here it should be a 1. And when S is 1, our output should match I1. So it should be a 0, 0, a 1, and a 1. So it's a plain old truth table, no magic. And we can, write a sum of products, or we can put this into a K-map, and we'll get lots of simplification because we have lots of adjacent ones. We can write an equation and implement it. But there's a different way we can write a truth table that captures this behavior more effectively. And so this is a different type of truth table. right? There's a truth table with just a pair of rows. And this truth table basically says, hey, if S is 0, X is equal to whatever I0 is. And if S is 1, X is equal to whatever I1 is. And we call this a compressed truth table. And we'll see a lot of compressed truth tables from this point forward. Because this makes it really easy to just look at this and see exactly what your circuit's going to do. Oh, if S is a 1, I don't care what's going into I1. Whatever's going into I0, that goes to the output. Right? We can get that out of this longer table, but we have to think really hard about it. This functionally describes what this circuit does. If S is 1, X is equal to I1. If S is 0, X is equal to I0. So when we compress a truth table, we kind of take some of the input variables and we move them to the output side of the truth table. So we'll see more examples of that in the next video. But this is a good first example. All right, so that's a 2-to-1 mux. There are bigger multiplexers. For example, we could have a 4-to-1 mux. And this would look like this. Four inputs, one output, and then two select lines. And the idea is, if we think of these select lines as a 2-bit binary number, if the number we input is 0, then I0 gets connected to the output. If the number we input is 1, I1 gets connected to the output, and so on. Now, if we write this as a truth table, we've got 6 inputs, 64 rows in our truth table. Very confusing. We can write this instead as a compressed truth table that looks like this. Right? 4 rows instead of 64, that's a win for sure. But the description of our behavior is very, very apparent from this truth table. If S1 and S0 are both 0, the output X is equal to whatever's coming in on I0. Right? It's building a connection from I0 to X. If S1, S0 are equal to the number 2, then X is equal to whatever's coming in on I2. And we have this connection from I2 to the output. Right? So it steers inputs into outputs. If you like, it chooses one input to connect to the output. And multiplexers are useful for a lot of things. For example, maybe we have a piece of our computer where we're going to do addition. So we've got an adder. And, you know, we've got to decide what the two things are that we're going to add. Well, maybe we want to add something from a register, you know, small internal piece of memory inside the CPU. Or maybe we want to add a value from our main memory. Or maybe we want to add some constant value. Or maybe we want to add, you know, some previous result from our addition, because we're doing a sequence of additions. Well, we could take these and we could put them into a 4-to-1, and we could take the output and put it in here, and we could have a pair of select lines. And so now if we're about to execute an instruction where we want to add the contents of a register to something, we could set our select line so that whatever's coming in on this part goes to the output of the mux and goes into the adder. Or if we want to add a constant like 1, we could set our select line so that this third line, which maybe has the constant 1 connected to it, goes through the multiplexer and goes into our adder. Or if we want to add the result of a previous addition, we could set our select line so that this fourth input, which is connected to the output of the adder, gets sent out back into the input. And this is how we program what happens inside a CPU, the sort of microarchitecture of a CPU. is by basically controlling how things move around in the CPU from input to output. So Engineering 270, we may dig into this a little deeper. We'll look at what's called the data path inside some CPUs and see arrays of multiplexers moving data around. So that's one thing that multiplexers are good for. Another thing multiplexers are useful for is building more multiplexers. So, if we wanted to build this 4-to-1 circuit, it's 64 possible input combinations. That's a big truth table, right? And we'll get some reduction when we do a K-map and cover adjacent ones. But there's a different way we can describe a 4-to-1 multiplexer. And it works by using a set of 2-to-1s. So we can do something like this. Take our inputs, put them into a series of 2-to-1 multiplexers. Connect these select lines together. Each of these multiplexers generates an output. Feed that into another 2-to-1 with another select line. And take the output from that and call that X. All right, and so I'm going to feed S0 into here and S1 into here. So 2-to-1 multiplexer, it's a pretty simple circuit, right? It's a few AND gates and OR gates. But if we take 3 of those 2-to-1 multiplexers and put them together like this, what happens? If our select line, let's look at S1, S0. Suppose our select input is 0, 0. Well, we have a 0 coming into these 2 select lines, which means this is going to take I0 and send it to its output, and this will take I2 and send it to its output. So we've got an I2 here, I0 here. Since S1 is a 0, this will take I0, send it to the output. But if instead my input is 0, 1, I would have a 1 coming in here. This would choose I1 and I3, and then S1 is a 1. That will take this, S1 is a 0. That'll take this input I1, and our output would be equal to I1. And you can work through all 4 cases and see that in each case your output will be equal to one of these 4 inputs based on the binary value of S1, S0. So we can build a 4-to-1 multiplexer out of 3 2-to-1 multiplexers. And if we wanted to make an 8-to-1 multiplexer, we could use a couple of 4-to-1s and a 2-to-1 and build it up like that. So we can make these mux trees, right, that select your inputs and filter them down to smaller and smaller sets of possible inputs, and eventually generates one output, which is your desired input. So muxes are great building blocks. So the counterpart to a mux is a demux. And a demux takes one input and sends it to one of many outputs. So for example, a 1 to 4 demux or demultiplexer would have one input, a pair of select lines, and then multiple outputs. And functionally it might have a behavior like this. So if our select line is 0, Y0 will be a copy of our output, and maybe all the other outputs will be 0. If our select lines have the binary value 1, then Y1 will get a copy of our input, and the other outputs will all be low. If our select is 2, then output Y2 copies our input, and if our select line is 3, then output Y3 copies our input. So there's a compressed truth table describing how a demux works. And we can put muxes and demuxes together, for example, to send information across a single line. So suppose we have 4 pieces of information. So our 4 to 1 generates a single output, and a 1 to 4 generates multiple outputs. And suppose we connect these select lines together. Well, if I set my select lines to 0, then whatever is coming in on line I0 gets sent to output Y0. And if I set my inputs to 1, 0, whatever comes in on line 1 is now being sent to output Y1. And if I set my inputs to 1, 1, whatever's coming in on input I3 is now appearing on output Y3. So with a single wire connecting these 2 blocks, I'm able to effectively transfer 4 bits of information from this side to that output side. But I do it in what we call time multiplexing. Over time, I change this pair of inputs so that first I send I0, and then I1, and then I2, and then I3. And this is also something similar to what we find inside a CPU, where we might generate the result from an adder and want to send that to different parts of the units. Well, we could use a demux for that. So these are also useful blocks, and this is one way where we can put a demux and a mux together and get some good behavior coming out. So let's look at a few examples of this back on engrcs.com. The first is a 74LS 138 or 139. This is a de-multiplexer, also called a decoder. If we look at the truth table for this, you can see it's got 3 select inputs, and it's got 8 outputs. And if our select inputs are all low, then output Y0 becomes low, and everything else is high. If our inputs A, B, C look like 1, 0, 0, so the binary number 1, then output Y1 is low, and all the other outputs are high. And it's low because our input G2 star is low. If our input G2 star is high, all the outputs are high. Doesn't matter what the select line is. So here they're using X's for don't cares on the inputs. So so what is this circuit doing? It's basically routing this input G2 star to one of our 8 outputs. Right, and the choice of output is based on these select lines CBA. So here my select lines are 0, 1, 0. That's a 2. So if G2 star is low, output Y2 is low. And if G2 star is high, output Y2 is high. And all of the other outputs are high. So slightly different behavior from the demux we developed here, where we made the other outputs default to a 0. For this chip, the other outputs are defaulting to a 1. But same idea, we're basically choosing one output to drive from, in this case, this input G2 star. So that's an example of a de-multiplexer. And if you go through the data sheet, so you can see the pinout and so on, but if you go through some of these data sheets for these bigger blocks, you'll actually find circuit diagrams for how these are implemented internally. And this looks like a bunch of product terms being generated. But we also see this thing I warned you about a few weeks ago, which is sometimes we see these bubbles or circles on the input side of gates. We can picture there's a little inverter sitting on each of these three inputs. Here's a triangle, the bubble's sitting over here. This is just a plain old inverter, but for whatever reason they've drawn it with the inverting part on the input side rather than the output side. Functionally, we just think of it as an inverter, um, but we'll see these different ways of drawing things. And if we take a closer look at this truth table for the 138, um, we notice that, if G2 star is high, the outputs are high. Everything else is ignored. And if G1 is low, the outputs are high and everything else is ignored. And the only time this chip does anything interesting is when G1 is high and G2 star is low. And then the output is based on what the select lines are. So G1 has to be high, G2 star has to be low. Well, G2 star is actually the OR of G2A and G2B. So for this to be low, both of these G2s have to be low, and then G1 has to be high. Alright, so G1 is high, G2 is low. If we go back up to the picture of the chip, and we look at G1, we see it's going into our chip as a straight line. G2, A, and B are going in with bubbles on them, right? So this is telling us that these are what are called active low inputs. So these are labeled enable. Normally if you have a line saying, this is an enable line, we would think, okay, enable, it's got to be high. Turning it high says, hey, let's go ahead and enable the chip. But since these have bubbles on them, these are active low. So to enable the chip, this has to be low, this has to be low, this has to be high. So that's just part of how we can start reading these diagrams of what a chip looks like and use that to start trying to understand how the truth table is going to work. But we can always go to the truth table and resolve any questions or ambiguities, right? This should always tell us exactly how the device is going to work. But as we work with more components and the truth tables get more complex, it may start to be easier once we've learned how to read these pictures of the chip with the bubbles on some inputs and outputs. That can give us the same information, but in a more direct way. All right, so another chip I want to look at, this is a encoder, and it's called a priority encoder. So 74147, and this does something interesting. If we look at the inputs, there's 9 inputs going in, and there's 4 outputs, and these outputs correspond to a number. And the purpose of this chip is to figure out, if we think of these inputs as having priorities, where input 9 is the highest priority, this circuit wants to find the highest priority input that is low. So if input 9 is low, 9 is the highest priority input that's low. If 9 is high but 8 is low, that's the answer to our question. 8 is the highest priority input that's low. And in that case, it doesn't matter what these other inputs are. But if inputs 9, 8, 7, and 6 are all high and 5 is low, then 5 is the highest priority input that's low. And these others don't matter. So the answer to our question should be 9, 8, 7, 6, 5, 4, 3, 2, 1. And the outputs give us the answer to our question, but they do it in a backwards way. When the answer should be 9, the output is 0, 1, 1, 0. Well, that's not 9, right? But if we think of low as being logic 1 and high as being logic 0, this is 1, 0, 0, 1. That's a 9. That's the answer to our question. If we think of low as logic 1 and high as logic 0, this is the number 1, 0, 0, 0, 8. That's the answer to our question. 8 is the highest priority input. And down here at the bottom, if we think of high as logic 0 and low as logic 1, then this is the number 0, 0, 0, 1. The answer to our question is input 1 is the highest priority input that's low, and sure enough, that's the situation here. Input 1 is low, all the other higher priorities are high. So this is another example of what we call negative logic, where we treat logic level high as meaning 0 and logic level low as meaning 1. There's nothing wrong with that, it's just different from the usual convention, but it's a perfect dual to what we do when we think of high as being 1 and low as being 0. It's just a different way of thinking about it. Alright, so this is a useful circuit for taking in a series of inputs that might correspond to, events that you want to pay attention to inside a computer, and maybe input 9 says the power has failed, and input 8 says, some calculation we were performing that's taking time, like a long multiplication, has just completed. And input 7 says a piece of information just arrived on the network interface. And input 1 might say the user has just pressed a key on the keyboard, right? Well, responding to a power failure is much more important than responding to a key press. Responding to the result of a multiplication is more important than responding to an incoming message on the network, because network traffic is relatively slow compared to the speed of our CPU. So as soon as our multiplication finishes, we want to save that answer and go on to the next calculation we want to perform. So we could use these things to get the attention of the CPU, and the CPU could use a circuit like this and say, hey, what's the most important thing that's happening right now? Someone got my attention. What's the most important thing I should deal with? And if it sees this, it knows, oh, the power's failing. Okay, I need to save the contents of memory somewhere where it won't be lost, and then I need to do an orderly shutdown. Or if the input generates this, it says, oh, somebody pressed a key. Okay, I can go deal with that because there's nothing more important happening right now. So this is something we'd find inside a computing system. All right. So last piece I want to talk about is something called a 7-segment display, and you may have seen these in TV or elsewhere. 7-segment displays are these little devices that basically contain multiple LEDs oriented in these horizontal and vertical directions, and they're set up so that by turning on certain combinations of these, you can make the display look like it's displaying a number, or in some cases a letter. So for example, if we turn on these 5 LEDs, we get a pattern that looks like this, and it looks like the number 2. And if we turn on these 3 LEDs, we get a pattern that looks like this, and it looks like the number 7. And so we can play with these devices in Tinkercad. And so we can drop a breadboard in here. And if we scroll down, I think we have to go to all components. And if we scroll down, we can find a 7-segment display that looks like this. And it's got some pins on top that are labeled, A, B, G, F, and E, D, C on the bottom. And so we can take this and we can pop it into our circuit board somewhere. And there's a pin labeled common and a pin on the bottom labeled common. And this is basically a collection of light emitting diodes, LEDs. And so we can think of this as, having an LED on the top and having an LED down here and another one down here and one in the middle, and so on. But rather than having 2 times 7 wires to connect to this, what they do is they take, for example, all of the output sides of the LEDs and they wire them together, and they bring that out to one pin, and this is called the common. And since it's the negative side of the LEDs, this would be called common cathode. And then they make the positive sides available for you to feed input signals to. So assuming I connect the common cathode through a resistor and then to ground, if I put 5 volts into here, this LED will light up, which is this segment right here. If I put 5 volts into here, then this LED will light up, which is this segment. If I put 5 volts into here, that would light up this LED, which is this segment, and so on and so forth. And so by controlling the inputs to, for example, the positive side of each LED and having my common cathode connected to ground through a resistor, I can light up different pieces of this display. And so we have a choice of having a common anode or a common cathode. I'm going to set this to common cathode. And there's 2 common lines, this middle pin up here and this pin down here. So let's connect those together. And I'll use a black wire for ground. Let's connect that to ground. But we have to do it through a resistor. So let me grab a 1K resistor and connect each of those common lines to ground. And by default, these resistors are 1 kilo ohm, which is exactly what we want. So let me go ahead and connect our common ground lines together and connect our 2 power lines together. And let's bring a power supply in. And let's connect this to 5 volts. And let's connect the ground output to our common ground rails. And so if I run this, right, nothing happens. We got 5 volts going in, but none of the displays are lit up. That's okay. So what we can do is we can take, for example, this pin right here, which is labeled G, and let's connect that to 5 volts. And now run our simulation, and you can see this middle bar is lit up. All right, so how do we know which LED is going to turn on? If we go to the data sheet for a 74LS47, right, so this is also from engrcs.com, it has a picture of a 7-segment display and the standard labeling for the segments. So segment G, that's that middle segment. Segment A would be the segment going across the top. So if we stop this and we get rid of that wire and we find the input for A, which I think is right here, so we can connect a wire between there and power, and we run our simulation, we can see the top bar gets lit up. So by making different combinations of connections to power, we can light up different pieces of this display. If I connect both A and G to power, that should turn on these 2 segments, and when we run that, we've got an equal sign. All right, so we could make a circuit that lets us put in a binary number and displays that number accordingly on this display. And it's a fairly complex thing to do. So if we look at what the 7 segments look like, suppose we have our inputs, let's just call them D, C, B, and A. And let's look at our 7 output segments, which we'll call A, B, C, D, E, F, G. And let me draw a picture here of what our display looks like. And these segments are labeled A, B, C, D, E, F, and G. And so if my input is all zeros, I want my display to look like this. I don't want that middle bar. I just want the outside. So I want G to be off, but I want all these other segments to be on. And if my input is 0, 0, 0, 1, I want my display to look like this, which means I want B and C to be turned on, but I want everything else to be off. If my input is 0, 0, 1, 0, I want my display to look like this, like the number 2. So I want to turn on A and B. I want C to be off. I want D and E to be on. I want F to be off. And I want G to be on. And so on. So I could design a truth table so that when I put in 4 bits, if I treat that as a binary number, I will get the corresponding segments lit up by generating these 7 outputs, which feed those 7 segments of the display. Big truth table, 7 circuits, 7 K-maps, 7 sums of products, a lot of work. Guess what? There's a chip that does that for us. That's the 74LS47. And you can see the truth table for this chip right here is telling us, for example, if our inputs are all low, then we want all of our outputs to be high except for G. So they're using on for 1 and off for 0. So that's that first row. If our input is 0, 0, 0, 1, what do we want? 0, 1, 1, 0, 0, 0, 0, right? That's this pattern right here. So this chip, this 7447, does exactly this task. It generates the outputs for A through G based on the 4 inputs. And, you know, somebody designed this. They made the truth table. They did the sum of products, and they came up with the circuitry. And this is what the circuit looks like. This is the circuit that generates the correct values for output A. And this is for output B, and so on and so forth. And when you make this truth table, the values that you get for these last 4 inputs, right? If you put in a number between 10 and 15, we don't really expect that to happen. This is supposed to display a single digit. And single digits mean numbers between 0 and 9. So when you make the truth table for 10 through 15, you can set those up as don't cares. And when you do that and you minimize and you come up with your equations, here's what this 7-segment display looks like for each of your inputs. For 0 through 9, you get these digits 0 through 9. For 10 through 15, you get strange things, right? This is not a digit. This is not a digit. This is just what the circuit that they implemented happens to display for 10 through 14, and 15 comes out completely blank. That was probably a design choice. And logically, we can look at this chip as follows. 74LS47, 4 inputs and 7 outputs. Now there's some other inputs here which are used for other things, and we don't need to worry about those, but the truth table will tell us what to do with those other inputs for all of these interesting combinations, right, where we're getting something meaningful on the display. This LT bar input is high. This RBI input does not matter. But the important thing is to set LT bar to be high. So we would want to take pin 3, tie it to 5 volts through a resistor, and then RBI doesn't matter, and RBO is an output. We don't care about that. This LT, by the way, that's a lamp test. And if you pull this this input low, then all of your LEDs turn on. So if you have, you know, like a scoreboard in a gymnasium and you want to know if one of the elements is burned out, you can drive all of these LT signals low and it should turn on all of these segments, right? Well, that's also what you get when you display an 8. But regardless of how else it's wired, if this LT bar input is low, all 7 segments should turn on, as well as, I believe, the decimal point. But we don't have a decimal point output here. But the 7-segment display in Tinkercad also has one additional input, which turns on the decimal point. And if we connect that to 5 volts, then we get that little dot lit up. So that's useful if you're building a calculator or something. All right, so 74LS47, very useful device to know about, and we'll use that in one of our labs where we actually build a 2-bit adder and display the resulting sum on a 7-segment display. So one more thing I want to just touch on in here, and we'll get into this more as we dig into some of the labs. But you know, when we design schematics for circuits, we do things in a very standard way. If we have an input, we might pull that input up through a 1K ohm resistor, and we make a squiggly line for the resistor, and we draw a switch like this, a little arrow going up. And we show the switch open, but we put a little dot here to say if you close the switch, this gets connected to this. And then maybe this goes into, you know, some piece of circuitry, and maybe there's something else here that feeds this, and this goes into, you know, something else, and these go somewhere, and maybe the output of all of this goes through an LED, which goes through a resistor and goes to ground. And we would label, you know, our inputs with letters and our outputs with letters, and these letters would match our system diagram and so on. And we always want to use these standard symbols for a switch, a resistor, power, ground, a NOR gate, an AND gate, an inverter. Those are standard symbols. But sometimes we're going to build circuits that incorporate things like, you know, a 74LS47. And when we do that, we don't want to draw a picture of the chip, right? Because if we draw a picture of the chip and we have something coming off pin 14, what does that mean, right? We'd have to pull up the data sheet to see what that looks like. So we're going to sometimes use just a box and use these labels like A, B, C, D, or lowercase a through G to symbolically show us what this chip is doing. And when we do that, right, we can put our inputs and outputs anywhere that we want around this box. So if I wanted to include a 74LS47, I might do something like this, right? Take this input, and I would draw a box. And I'd say, you know, something like, you know, U5. And up here in U5, we have a 74LS47. And we'd list the power and ground connections and so on. But over here, I would say, what's the name of the input that this is connected to? So maybe this is connected to input, you know, B. And maybe this output here is segment A, and this is segment G. And maybe I'm taking those and connecting them to 2 inputs of this NOR gate. Now, this is not something we would do, right? Normally, these just go to a 7-segment display. But as an example, right, when we have a more complex logic block, we're allowed to represent it with a rectangle, label it with a designation like, you know, U1, U2, and then just label the inputs and outputs with the names from the data sheet. So for example, A, B, C, D, or if we were using a priority encoder, we could label these with, you know, input number 1 through 9 and output A, B, C, D. So we'll explore this in some of the practice problems and in some of the labs. But we definitely do not want to draw a picture of the chip, right? We do not want to draw something like this and then force our connections to go into these pins. That's just going to make the picture really hard to draw, hard to follow, and it's not going to tell us anything unless we pull up the data sheet and see, oh, you know, pin 1, that's the input B. Okay, so I guess this wire is going to input B. No, just label it and draw your wire to it. And you know, if output G happens to be over here, you know, I can put it on this side of the rectangle so it comes out there. There's no need to bring my wire around over to here, right? So we want to make these things easy to read, and we want them to convey information about the behavior of the circuit. So for logic gates, switches, LEDs, resistors, ground, power, we use the standard symbols, right? But for these more complex blocks like the 7447 or the priority encoder or a half adder or a full adder, we can go ahead and we can just draw a rectangle and label the inputs and outputs based on the function that they're performing. All right, that should do us for this lecture. So in the next lecture, we're going to kind of wrap up this part of the course. We're going to talk about NAND and NOR gates and a cool feature of them, which is called universality. We'll talk a little more about compressing truth tables. We'll talk about programmable logic. So more advanced types of circuits called PALs, PLAs, and PROMs that we can actually configure to do different tasks for us. And then we're going to start looking at more of the real-world behavior of these devices. And we're going to pull up some data sheets and look at how these devices respond in the real world when we change an input, what actually happens to the output, and when does it happen. And that's going to lead us to thinking about the timing of operations in our circuits. And that's going to be the gateway to introducing circuits that have a memory. And that's going to be the second piece of the course, is circuits whose behavior can't be defined by a simple truth table, but instead the behavior depends not only on the current inputs, but on what's happened in the past. And that's where we start developing what are called state machines. All right, so that's all coming next. Thank you.